Hello. Today's lecture is going to be about circular motion and in particular centripetal acceleration. Our objectives today are to be able to describe and identify uniform circular motion. From there we'll be able to calculate the magnitude and direction of centripetal acceleration and compare and contrast the term centripetal force with net force as well as other forces. Okay, first off, uniform circular motion is what we're going to be analyzing during this unit. Okay, and each word has a meaning, and so we don't skip over that. Okay, the term uniform means that the object is moving at a constant speed. You need to be clear that this does not mean that it is moving at a constant velocity, because it is certainly not moving at a constant velocity. Velocity is a vector, and so it has both magnitude and direction. Constant speed simply means that the magnitude of your velocity vector is not changing. Clearly, if you're moving in a circle, your direction is changing. Okay, circular, the second word in that phrase, simply means that the object is moving in a circle. This also includes various curves, because we can describe a curve as being just a section of a circle. Okay, and motion clearly means that the object is moving. So when the object is moving and going in a circle, it's changing direction. As a result, it has a change in velocity, and if there is a change in velocity, Newton's laws tell us that there must be an acceleration. Okay, Newton's first law says the object in motion will continue in motion at the same speed in a straight line unless a net force acts on it. Well, this is not moving in a straight line, so that means there must be a net force. And that net force is given by the sum of the various forces acting on the object. Okay, or using Newton's second law, acceleration is equal to net force divided by mass. Okay, when we're talking about circles and uniform circular motion, we actually have a second formula to help us solve for that acceleration. Okay, the diagram in the lower corner shows you that acceleration is given by v final minus v initial over delta t. So that's basically change in velocity divided by the change in time. And clearly with my two different velocity vectors, v2 and v1, I do have a delta v. And the direction of that is going to be pointing directly towards the center of the circle from wherever the object happens to be. Okay, so if I happen to be over on this corner, okay, if I happen to be over here, directly towards the center of the circle is that direction. Or over here, it would be in that direction. On the bottom, right there. Okay, so it always points towards the center of the circle. The magnitude of this acceleration is going to be given by v squared over r, where v is the speed of the object. Okay, linear speed. How quickly is it going around the circle? Okay, so we have this formula. Let's do a sample problem. Okay, I have a horse on a carousel that's located 5 meters from the center. Okay, so center, r is the distance to the center. So in this case, my distance is 5 meters. And the horse has a linear speed of 6 meters per second. Okay, so here we have our velocity is given as 6 meters per second. And what is the horse's acceleration? If you're wondering why I have the term linear speed, okay, linear speed is differentiated from angular speed or angular velocity. Okay, angular speed is how quickly is it going around the circle, kind of. And it's irrespective of the distance. So it doesn't matter what the radius of your circle is. You're going to cover so many degrees per second, or so many radians per second. Okay, so in this case, since I'm trying to find the horse's acceleration, and I'm given that it's going in a circle, or at least carousels we're familiar with go in a circle, so a centripetal acceleration is equal to v squared over r, or 6 squared divided by 5, giving me 36 over 5, or 7.2, and it's the same meters per second squared. Okay. So that brings me to the centripetal force. Okay, this is not a term that I'm very happy using. Okay, centripetal force gets confused a lot of times. Okay, because people hear the term centripetal force, they hear gravitational force, the normal force, and they think that this is a force just like those that I just talked about. Okay, however, it's not. Okay, there is no such force as centripetal force. Those forces, okay, normal force, gravitational force, um, all belong to the realm of real forces. Okay, there are two objects associated with every force, um, and there's a Newton's third law pair between them. Okay, the gravitational force is the force of Earth on the object, and there's a Newton's third law pair that says the force of the object on the Earth. In the case of centripetal force, there isn't always, okay, going to be something, two objects associated with it. In the example of my flying pig, okay, there was no second object. Okay, the force was towards the center of the circle, but there was nothing in the center of the circle. Okay, so that's why centripetal force is a bad term, because what we describe as centripetal force is really just the net force. This is nothing more than F net. Okay, so if I do F net equals ma, as down here, okay, really what I'm saying is F net is going to equal mass times the centripetal acceleration. Okay, or we can make the substitution and call it mv squared over r. Okay, you must be very clear, okay, we never draw a centripetal force on our free body diagram. Okay, you don't draw an arrow on your free body diagram and label it F sub c. That would be completely incorrect because there is no such force. That's not to say there won't be a force towards the center of the circle. There must be a real force, okay, either the string or the force of gravity making the moon go in a circle, okay, but those would be labeled F sub g for gravity or F tension for the string. So don't label your free body diagrams with centripetal force. If the centripetal force shows up anywhere, it's simply that we describe it as acceleration. Okay. So here's a continuation of my example. Okay, it's the same 7.2 because it's the same 5 meters and 6 meters per second. Okay, but now I give you a mass and I want to know what is the centripetal force acting on the horse. Okay, well, centripetal force is the same thing as net force, so I'm just going to do mass times my acceleration, or since I know what my mass is, that's 22 kilograms, times the 7.2. I'm going to end up with 14.4, 144, 158.4 newtons, or taking it down to 2 sig figs, 160 newtons. Okay, so that's the net force acting on it, okay? Just because I asked for the centripetal force, you need to be able to say, well, centripetal force, all I'm asking for really is the net force, okay? And that brings me to an even worse term than centripetal force, and that would be centrifugal force, okay? We should never ever use this term centrifugal force, okay? Yes, I'm aware that in the chem and bio labs we have a device that's called a centrifuge, and it spins really fast, and any sediments or, you know, it effectively separates solids out of your liquids. So we think such a thing exists, okay? However, centrifugal force does not exist, okay? It's really what happens when we envision Newton's first law, okay? The diagram on the bottom shows a car going around a curve and there's a tape on the dashboard, okay? The tape and objects in the car, okay, really want to go straight, okay? That's Newton's first law. An object in motion will continue in motion at a constant speed and in a straight line. What's really happening is that the car is turning under that object. Okay, so even though the car is turning, it's not providing a force on there, okay? But from the perspective of the tape or the perspective of a passenger in the car, it feels like they're being forced in. That really doesn't happen, though, until they hit the side of the door. Okay, you can imagine how dangerous this would be if you weren't wearing a seatbelt and your door was open and you're going around the curve at really, really high speeds. Okay, at that point, there's a high probability that you're going to be ejected from the car because you're going to go in a straight line, and if there's no door to stop you, you're going to end up being thrown from the car. Okay, so centrifugal force is a bad term. A lot of journalists end up using it, and I really have concerns over how well they did in physics when they took physics, if they took physics. But it sounds like such a nice term, centrifugal force. But we are going to try to avoid using that term ever. Okay, centrifugal force implies that there is a force to the outside of the circle. There really isn't. It's just that everything under you is turning to the left, while as you want to go straight. Okay, so I'm just going to finish this lecture with a thought question that we'll talk about next time. Okay, I have a ball and I'm whirling in a circle. Okay, much like Wilbur my pig, it's going around in a circle, and this is a top view, so it's a horizontal circle. Okay, and at some point, for whatever reason, my string breaks. Okay, at point P, and I wonder what will be the path of my ball. Okay, if that was the case. Okay, is my ball going to go straight outwards? Okay, is it going to go off at an angle? Is it going to go that way? Or is it going to continue its circle but, kind of spiral outwards? Okay, that's what we're going to talk about the next time. Thank you.